Hello everybody, welcome to this second chapter of nanoelectronics. Today we are going to talk about materials, as we anticipated last time, and we also said last time that for this course and in order to understand how the devices we are interested in work, we need to understand how the three fundamental types of materials, of electronics materials we know of, work and understand them. So these three basic types of electronics materials are insulators, for example glass, semiconductors, for example silicon, and conductors, for example copper. Now this categorization can be understood using a very simple definition, an empiric definition, that is that at room temperature insulators have a resistivity of bigger than 10 to the 8 ohm per centimeter. Conductors, on the other hand, have a resistivity that is much smaller than 10 to the minus 3 ohm per centimeter or so. And semiconductors are all those materials whose resistivity will fall in between these two values. Now please note that the resistivity is an intrinsic property of a material, of any electronic materials, and quantifies the difficulty that charge carriers have in moving through these materials under the effect of an external electric field. An electric material is generally defined as an insulator that is made up of atoms that can be polarized under electric field. And finally, a metal is generally a conductor that is characterized by the fact that it is quite malleable. Now, as physicists, though, we could move on and consider more quantitative, if you like, definition for these three categories of materials, and using basically quantum mechanics and band theory of solid-state materials, what we could actually say is that we could categorize the conductors, insulators, and semiconductors using what we call the band gap of the material. So we can use this very nice graph here to represent the energy levels of a solid made of a certain material, and then we could realize that all the band diagrams of all possible materials could be categorized in this way. So there are those materials whose band diagrams present a gap between the topmost full energy level and the bottommost empty energy level. And if this gap is bigger than 4 to 5 eV, then we will say that maybe this material behaves as an insulator. If that gap is a bit smaller, of the order of 1 eV, then we could say that this material is a semiconductor. If, on the other hand, there is no gap between the topmost full energy level and the bottommost not full empty energy level, then we would say that this is a conductor. Okay, so we said that in this chapter we are going to actually revise concept. So I hope that most of these things that we are going to discuss are things that more or less you've come across in the last few years. So here let's have a look at the Ohms Law and generally what current means, the definition, and so on. So if we have a piece of material as the one that shown here, it's imagine a cylindrical piece of material with length L and cross-section area A, and imagine that we apply a voltage across the two ends in this way, so the voltage on this end is higher than the voltage on this end, so this immediately creates an electric field that goes in this direction, and the electric field is given by V over L, the intensity of the electric field. And so if there are positive free charges in this piece of material, they will move in the direction shown here, in this direction, and so we can define the current flowing through this piece of material as I equal the amount of charge flowing through the cross-section A over the amount of time that it took for that amount of charge to go through. So dq over dt. The units are the ampere, and the ampere given this definition is equivalent to 1 coulomb per second. Now, from the definition of current, we can then define also the current density, which is simply defined as the current density, the current intensity over the area that this current is flowing through. So J is I over A, and the units obviously of J is ampere per square meter. Okay, so from this definition of current, then we go to Ohm's law, and the realization is basically that J depends on the electric field intensity, or in other words, the current depends on the voltage applied, and the Ohm's law is simply depicted here with this formula here. This is probably the form that you know better. V equal R times I, where R is a characteristic of the material. It's called the resistance of the material, and the units are the ohm, which is volt over ampere. We can equivalently define the same law using electric field and current density, and this would take this form here, E equal rho J, and the units rho would be the resistivity of the material, and its units are given in this formula here. So it's in the end there is units of the resistivity is ohm per meter. Now remember that the resistivity is an intrinsic property of the material. It has nothing to do with the geometry of the material. So as we are this formula here below shows exactly that. So we can see that, and this actually goes under the name of the second Ohm's law, and we can actually demonstrate through these very simple steps that R is actually related to rho, the resistivity, through this formula. R is equal to rho times L, the length of the conductor of the piece of material, over A, its cross-section. And so this formula basically shows that R, the resistance, is made of two components. A component, rho, that is a characteristic property of the material, and a fraction L over A, which is actually related to the geometry of the material itself. So it is also useful to define the inverse of resistance and the resistivity. So the inverse of the resistance is called conductance, as indicated by G, and the unit is obviously ohms to the -1, which is for simplicity called Siemens, and rho, the inverse of rho is the conductivity, and the units are Siemens per meter. So here we can see Ohm's law in the using the resistance, and here we see Ohm's law in using the conductance and also the conductivity. So remember that the relation rho is 1 over sigma and R is 1 over G, or the opposite. G is equal 1 over R and the sigma is equal 1 over rho. Just for example, let us have a look at some resistivity values of some materials. So we see here, for example, some characteristic metals. Silver, copper and gold, they have resistivities that are extremely small, of course, they are conductors. And while on this other side we see materials that are, for example, glass is, we know very well, is not a conductor, is an insulator, and the resistivity is extremely high, so 10 to the 10, 10 to the 14 ohm per meters. While graphite and silicon are examples of materials that are somehow in between. They're not really conductors, but they're not also pure insulators, so they fall somehow in between. Now, it is very important to remember that resistivity or conductivity is the same, are strong functions of the temperature. And the way they depend from temperature actually depends also from what type of material we are dealing with. So for example, if it is a metal, the resistivity will increase with temperature. Or here on these graphs, we are assuming that this is the 0 Kelvin point. If it is a semiconductor, it will decrease with temperature. While if it is a superconductor, there is a temperature below which the resistivity basically goes to 0. This temperature is the critical temperature, Tc. Okay, so basically a superconductor is a very special type of conductor where below a certain temperature the material has basically no resistance at all. The resistance is 0, so electrons move free, charges maybe move freely, completely freely within the material. So just to remind ourselves some fundamental laws and concepts. So when we have resistors that are in series, then the equivalent resistor is given by this formula here, by obtained simply by adding all the resistances at play. On the other hand, if we have resistors that are in parallel, as in this circuit here, then the equivalent resistance is given by this formula. So the inverse of the equivalent resistance is equal to the sum of all the inverse resistances. Okay, let's have a look now to dielectric materials. So we already anticipated that the electric material is an insulator, and that under an applied external field, electric field, the material can be polarized. This means that under the influence of this electric field, electric dipoles are formed, and these orient themselves along this electric field. These dipoles may be of different type, so can be electronic, so due to a rearrangement of the electronic cloud around each single atom in the crystal, on the material, and so on and so forth. And we will see that these different types of dipoles also arise when the excitation, the electric field that is triggering this effect, have specific frequencies. We will discuss this better in more detail in a moment. But what is important here to note, as it is depicted in this picture, so if we take two parallel plates and we apply here positive voltage, here a negative voltage, so that the applied electric field goes in this direction, then the material that is between placed, if we place a material between these two plates, then the electric dipoles are generated as shown here, as this one here, for example, with a positive charge on this side, because the positive charge is attracted by these negative charges here, and the negative charge on this side because this is attracted by the positive charges there. And so this is the type of polarization we are talking about. And what basically happens in the end is that because these dipoles are very, very close one another, we can easily see that effectively these positive charges here and these negative charges here cancel each other. The same we can say here, these positive charges here cancel these negative charges here, and the same here, these positive charges here cancel these negative charges here. And so in the end we are left effectively with positive charges on one end and negative charges on the other end of the material, and this is called polarization. This is a result of the polarization of the material. But the final result is that because we have positive charges at this point and negative charges at this point, basically this means that there is an internal electric field due to polarization, EP, that goes in this direction. So this is the fundamental part of the polarization of the electric materials that we need to keep in mind, and we will have a look at this in the next few slides. So before we look in more details to the electric materials and polarization and so on and so forth, let us remind ourselves what do we mean by capacitance. First of all, let us define what do we mean by a capacitor. So the simplest one we will see in a moment is the parallel plate capacitor. So this is simply made by placing two metallic plates in front of each other with a certain separated by a certain gap. So if we take this device, this type of capacitor for example, and we connect the two terminals to a battery, some charge will be presented to one plate and the opposite charge will be presented to the other plate. I should remind you that the two charges that are presented at the two plates are the same in magnitude because of induction, electrostatic induction. And so if we imagine now to double the amount of charge, the electric field becomes twice as strong. And so this means that also the voltage across the device is twice as large. So is this realization actually that tells us then that is the ratio between the charge on the plate and the voltage across the device that is actually a constant. And this constant is called capacitance. So every capacitor is characterized by its capacitance, C, which is defined as the ratio between the charge and the voltage required to place that charge on the plates. And the units for the capacitance is the farad, where 1 farad is defined, given that definition, 1 coulomb per volt. Okay, so let's have a look more in detail to the parallel plate capacitor in vacuum. So these results are probably results that you know of. I'm just putting them here so that you have everything in one place. You must have probably seen these things in the last few years during your course of studies. First of all, let us define charge density. So the parallel plate capacitor is, as we said, made by two metallic plates separated by a distance d in this case. So the area of the plate is A, so we can define the charge density, surface charge density sigma, which is Q, the amount of charge we placed on the plate divided by the area of the plate. So we can demonstrate using electromagnetism that the electric field within the two plates is given by sigma over epsilon zero. Epsilon zero is the dielectric constant of vacuum. It's a fundamental constant, and so we can write the electric field in this way. Now, if we recall that we have, in order to create a charge Q and minus Q on the two plates, we have had to apply a certain voltage between the two plates. Then we know that that voltage is given by E times D, where D is the separation between the plates. So using the above results and substituting the symbols, we get that VAB is given by the voltage across the device is given by this formula. So we have here a relation that relates the charge Q and the voltage across the device. So if we take the ratio, we can calculate the capacitance of this device. So C is equal Q over V. And in this case, according to the above results, is given by epsilon 0 times A over D. So A is the area of the plates and D is the distance between the plates. So this is a very nice little formula that gives the capacitance of the parallel place capacitor in vacuum. As we did for the concept of resistance, here we can see what happens when we put capacitors in series, for example, and the equivalent capacitance in this case is given by this formula. We have to the inverse of the equivalent capacitance is equal to the sum of the inverse of all the other capacitances. While when the capacitors are in parallel, the formula to use is this one here, where the total capacitance is actually the sum of all the other capacitances. Okay, this is just to remind you some fundamental results. So let us now have a look to what really happens when we put some material between the plates. So let's see how polarization affects what we've seen until now for the parallel plate capacitor in vacuum. So let us start this hypothetical experiment, let's say, considering a parallel plate capacitor that is in vacuum and is being charged with a certain charge, and the surface charge is sigma on this plate, which is positive, and minus sigma on this plate, which is negatively charged. So let us now imagine that we insert a dielectric material into these two plates. So what we notice is that the electric field, which in the case of the capacitor that was in vacuum, the electric field is 0. Then the electric field now, once we insert the material, lowers, and the new electric field is 0 divided by a certain constant K, which depends on the material. K is obviously a positive number bigger than 1. Okay, K is bigger than 1. Okay, K is 1 obviously only if the material we are inserting is actually vacuum. So the reason why the electric field between the plates is changing is because of polarization, as we briefly described already a few slides ago. So we can understand all this by looking at this diagram here. So initially we said the electric field in vacuum is given by E0 is sigma over epsilon 0. But once we insert the material, we have some polarization of the atoms in the dielectric material, so we have a certain induced negative charge and some induced positive charge on the other hand. And because the induced positive charge faces the originally negative charge present on the plate, this means that effectively on this end the total charge is smaller, so the total negative charge is decreased by the presence of this positive charge, and the same happens on this end. So the total positive charge is decreased by the fact that there is some negative charge now there. So the new electric field is smaller, and it can be expressed in these terms. Or qualitatively, obviously, we can also just look at the direction of the fields. So E0 goes in this direction, the induced electric field due to polarization goes in this direction. It is obviously a little bit smaller. So the total electric field is still in the direction of E0, but is a bit smaller. And this is put into a formula in this way. So E, the total electric field now, is given by sigma, the original surface charge, minus the induced electric surface charge, divided by 0. And we know that, as we said previously, this must be equal to E0 over K. This is an experimentally observed result. And so from this formula we can now do two things. Either we can express or calculate the amount of induced charge this way. We have to recall that E0 obviously is sigma over epsilon 0 here. Or what we can do is to use this relation to obtain basically this result here. We can probably do it here. So we said that E is equal to E0 over K, but we know that E0 is by definition sigma over epsilon 0. So we can write the new electric field as sigma over epsilon, where epsilon is the dielectric constant of the material, which is the dielectric constant of vacuum time K, which is this constant that we introduced previously, which we will call the relative which is also sometimes indicated as epsilon r. So going back to the parallel plate capacitor in presence of a dielectric material, so we just demonstrated that we can again write the electric field using a form that is very similar to this, but simply now we have to replace epsilon 0 with epsilon. So epsilon is the dielectric constant of the material, which is defined, which is represented in this, given by this formula, epsilon equal K, the relative dielectric constant, time epsilon 0. And we can also now calculate the new capacitance of the capacitor in presence of a dielectric material between the plates. We can demonstrate that then the capacitance of this device is K time the capacitance of the corresponding capacitor in vacuum. And so the formula becomes basically this one here, or simply this one here. So we can use the same formulas that we have seen for the vacuum case, we can use the same formulas also in the in presence of the electric material. Simply remember that you have to replace epsilon 0, which is the dielectric constant of vacuum, with the dielectric constant of the material. Okay, here this slide shows what we've already said in several ways, what microscopically polarization means, and how the positive and negative charges are induced in the end at the two ends of the material once the material is placed in a constant electric field like this one. So this induces charges, as we said, at the two ends, negative and positive effectively, and internally an electric field that is induced by the external one. Now, so the situation we've just described a moment ago represents what we would call the static case, where we have a constant electric field, uniform, and the material polarizes, and so on and so forth. Now, we can consider also the case where the electric field is not constant over time. It can, for example, change. It could be, for example, a periodic signal with a certain frequency. And so we could consider the dynamic case, or also that we could call the case for alternating currents, where we will see, and this is what we will see in this slide, that what responds to this electric field is not always the same thing. So polarization can take different forms. In order to understand this better, we could, for example, consider that this is our capacitor. Let's call this point A and point B. So imagine that now our electric field is generated, obviously, as usual, by a voltage applied across our device. So let us plot here the voltage across the device, which we define as VA minus VB. And let us imagine that this is like a sinusoidal form, this type, and this is time. So if we consider, for example, this moment in time, which we call T1, VAB is obviously positive, so this means that VA is bigger than VB. So VA is bigger than VB, so we have a positive value, a higher value of the voltage here, of the potential, and a lower value here. So this means that the electric field is directed in this way, in this moment. While if we take another moment in time, for example this one here, we call it T2, so this was at T1. At T2, the electric field would be directed in this way. So we can see that in the dynamic case, so in presence of alternating currents applied to our device, our capacitor, the electric field can switch direction. So it is actually the frequency of this signal that becomes very important now. And the reason why it becomes important is in a way represented in this plot here. So in this plot, what we can see is that when the frequency of the electric field of the voltage applied across the device is extremely high, then nothing can effectively respond to this electric field, to this excitation, and so the material is effectively invisible, and the dielectric constant is that of the material is effectively that of vacuum. But what happens is that as you now decrease the frequency of the signal that you are using to excite, let's say, the material, what you see is that at a certain point, the first thing that will start to respond are the electrons. They are small, they have a very small mass, and so they can move very fast. So they are the first that can respond to this very high frequency electric field that is applied to the device. And so we have a first contribution to the polarization, to the total polarization, and this is due to the electrons. As we keep decreasing the frequency, something else may start responding, and this is ionic polarization. So ionic polarization is due to ions that are present within the material that can somehow move. As is depicted, this is depicted in this here on the left, with this spring between a positive and a negative ion, so on and so forth. There are several factors that may contribute to the polarization we have inside our material, and one of these, a very important one, is actually the frequency we are using to excite, if you like, our material. Okay, one more practical example relating still to dielectric materials and capacitors. Let us consider the dielectric stack. So this is an application of what we've just seen. So in this case, a dielectric stack is a capacitor that between the two plates has effectively two different materials, material 1 and material 2, with different, obviously, dielectric constants. We can say that this material has a relative dielectric constant K1 and this material has a relative dielectric constant K2. So in order to, and the question is, what is the total capacitance of this device? Or maybe which is the equivalent relative dielectric constant of this device? So in order to approach this problem, we can simply realize that this is equivalent to the series of two capacitors, C1 and C2. C1 with material 1 and C2 with material 2. And so we know how to calculate the total equivalent capacitance here. We use obviously this formula, and if we recall that C is epsilon 0 times K times A over D, we can replace the capacitances with the corresponding symbols. We can remove the common terms, which obviously is A and epsilon 0. So in all these capacitances there will be an epsilon 0 and an A, so we can simplify that, and so we have this simplified version of the formula. And from this formula we can calculate K total, so the effective total dielectric constant of this stack of two dielectric materials, which is given by this expression here. Okay, so up until now we have considered our dielectric material as an ideal material. This means that we've always been assuming until now that this material has an infinite resistivity. In reality, real dielectric materials have a finite resistivity. So this means that a real capacitor with a real dielectric material in between will have a finite resistivity. So will be characterized by a certain K value, a relative dielectric constant, and a certain finite resistivity. This means that this symbol here is not equivalent to this one, to the ideal capacitor, but is actually equivalent to a slightly more complex circuit that is a capacitor, an ideal capacitor, in parallel to a resistor. So a real capacitor is actually an RC parallel circuit. Just to note here that this is a very, very, very super simplified approach that we are taking here. Things can be much more complicated, much more complicated. But for the sake of this discussion we are doing, it's completely fine. So the RC is the simplest model we can use for a real capacitor. So what does this mean? Well, we've just said that the signals we may apply to our capacitors are not always static signals, so DC signal, direct current signals, but in general we should consider the more general case of a dynamic case, that is alternating current signals. So where one important parameter is obviously the frequency of that signal. So let us assume we are in this situation. So you may know that in this situation, in order to analyze what a circuit does, we need to use the concept of impedance that generally is indicated with the letter Z. Now we can demonstrate that the impedance of a resistor R is R, and the impedance of a capacitor is 1 over j omega c, where j is the imaginary unit, omega is the angular frequency, which is remember that omega is 2 times pi times f, where f is the frequency of the signal we use, and c is the capacitance of the capacitor. Okay, so this means that the impedance of this RC parallel circuit is actually given, well, if you follow this these equations here, is given by this formula, where omega 0 is a characteristic frequency which is given by a characteristic angular frequency which is given by 1 over RC. But most importantly, this formula is telling us that if omega is much bigger than omega 0, which in other words we can translate in when we are at high frequencies, the impedance of this RC parallel circuit is actually equivalent to the impedance of the capacitor, and so this circuit behaves effectively as a capacitor. When though the angular frequency is much smaller than the characteristic frequency omega 0, that means in other words that we are at low frequencies, then the total impedance is actually equivalent to the resistance, and so effectively our real capacitor has actually a resistive behavior. It's not anymore a capacitor. So this is very interesting and very important, especially when someone has to use the real capacitor to design some application. Just to conclude then this part about real capacitors, so and summarize. So we said that at high frequencies a real capacitor effectively behaves as a capacitor, but at low frequencies it doesn't and behaves as a resistor. And here we can use our known results that C we know that C is the capacitance C is equal to epsilon 0 Ka over D. On the other hand, using Ohm's law, we know that R is rho, the resistivity of the material, time D, which in this case D is the length of our piece of material, and A is the cross-section of the material, so is the area of the plates in this case. So if we use these two known results and we put them into the definition of the characteristic frequency omega 0, 1 over RC, we get this very nice, compact, beautiful formula, which is particularly beautiful because we can see that this characteristic frequency omega 0 depends only from fundamental constants that are characteristic of the material, no geometrical properties involved. So rho and K. So from this point we will now continue our course having a look at semiconductors, and so trying to revise some of the fundamental concepts about semiconductors. So what we need to fundamentally remind ourselves is that semiconductors have a tunable resistivity, and this resistivity depends on temperature, irradiation, and doping. This is represented very nicely in this graph, where we can see that on one hand we have metals that are conductors and that have resistivity that is extremely small, 10 to the minus 6, 10 to the minus 5, and so on. On the other hand, we have insulators that have a very large resistivity, 10 to the 10, 10 to the 12, and so on and so forth. And so in between are semiconducting materials like germanium, silicon, and other more complex alloys, whose resistivities are, can cover quite a wide range. And the reason they may span such a large range is because of all these factors we just mentioned. So it depends from doping, temperature, and so on and so forth. Okay. In this slide, we can have a look now at the position of some known semiconducting materials, like silicon, for example. We can see that silicon is placed in the fourth group. So this means that silicon has 4 valence electrons. By contrast, boron is in the third group, so it has 3 valence electrons, and phosphorus is in the fifth group and has 5 valence electrons. So we will I'm pointing this out at this point just because we will come back to this in a moment, and we will use this information when we will discuss doping. So silicon, as we said, has 4 valence electrons, which means that if we take silicon as on its own as an atom, the electrons will be arranged in this way, so 2 electrons in the s orbital and 2 electrons in the same p orbital. But when we put silicon in a crystal lattice, then energetically it is more favorable for silicon to hybridize those orbitals in a sp3 hybridization. In this way, silicon has effectively the capability to bond, to create 4 bonds with 4 neighboring atoms, which are other silicon atoms, of course. And so here we can see how we represent this silicon crystal with double bonds due to the fact that each of these lines represents effectively an electron that is being shared between 2 neighboring silicon atoms. So 2 lines indicate 2 electrons that are being shared in a covalent bond. In the next few slides, we will remind ourselves some fundamental results that are aimed to remind ourselves why temperature, irradiation, and doping change all these things. So the first one is quite simple. So why temperature is important? Temperature is important because if you increase temperature, electrons that are in the valence band can acquire enough energy to jump into the conduction band. So as simple as that. From the quantum mechanical point of view now, we can describe things using the Fermi function. So you may have seen the Fermi function in your quantum mechanics course. So the Fermi function is a probability distribution function, and this has the mathematical form is this one here. And this function provides the probability to find an electron in a state that has this energy E. EF is the Fermi energy of the material, we would say in this case. The theory behind the Fermi function deals with the fermions, and an example of fermions are obviously electrons. So they are dealt with as they were a gas of electrons. So the concept of the Fermi function arises from that approach, and we will see later on that it can be demonstrated that the Fermi level in our semiconducting material generally is very close to for materials that are undoped, is generally very close to the midpoint of the band gap. And what we can also demonstrate is that this quite complex formula simplifies quite a lot if we are reasonably far from the Fermi energy. So if the energy of the state we are considering is far enough from the Fermi level, far enough means is quite bigger, few times bigger than kT, the thermal energy, then the Fermi function can be simplified to just the Boltzmann distribution effectively. And so in presence of semiconducting material that has a valence band, conduction band, with the Fermi level, as we said, more or less at midpoint, this difference E minus EF effectively is generally of the order of half the band gap. And that's why that here we've simplified even further our formula and wrote it down basically in this way. So so this formula is telling us that the probability to find an electron, for example, in the conduction band is exponentially dependent from the band gap. So this means that the conductivity of the material is also exponentially dependent on the band gap. Obviously, the more electrons we have in the band gap, the more conductive is the material. So that's how we produce this result. And obviously, because the conductivity is defined as the inverse of the resistivity, we can also say that the resistivity also depends exponentially from the band gap. Obviously has an inverse dependence. So if we increase the band gap, the conductivity will decrease, because there's in the exponential here we have a minus at the exponent. At the same time, obviously, the resistivity grows exponentially if we increase the band gap. Okay, just to conclude on this point, on the quantum mechanical view of what really happens with the temperature. So if we are at 0 Kelvin, the Fermi function is effectively a step function and has this form here. So the green curve. So for energies that are below midpoint, remember that this is effectively the Fermi level, as we briefly anticipated. So for states that are below the Fermi level, the probability to find these states occupied by one electron is effectively 1. So this is 1. But when the state is above the Fermi level, so for states that are, for example, in the conduction band, then the probability becomes 0. Okay, so a perfect step function. If we now increase the temperature, what happens is that this step function changes to a much smoother curve. And so there is now a finite probability to find some electrons here. So these electrons that lie below, if you like, this curve are electrons that have been promoted from the valence band here to the conduction band. Now, another important concept we should remind ourselves is that in electronic materials, the charges that move are obviously electrons. But in reality, when we consider conduction and valence band, we immediately realize that it would actually make a lot of sense to actually introduce in the picture also a quasi-particle that we will call holes. Indeed, we can see that when an electron in the conduction band moves, in this case is moving in this direction, correspondingly there must be a hole in the valence band that is moving as well. So we are effectively introducing here a quasi-particle that is actually a position where there is no charge, that we call a hole, that we will use in our formalism to describe things. So while conduction in the conduction band is very well represented obviously by the movement of electrons, the conduction in the valence band is better represented by the movement of holes. And so we will indicate the density of electrons in the conduction band by the symbol n, while we will indicate the density of holes in the valence band by p. Oh, in the case of undoped materials, the number of electrons is n is equal to the, obviously, to the number of holes for charge neutrality. So we can already anticipate that n is equal to p in materials that are not doped. But we will come discuss in more detail this in a moment. Okay, we also said that another factor that is important is in order to manipulate, if you like, the resistivity of semiconductor materials is electromagnetic irradiation. And we are particularly interested here, for example, to visible light. And from this diagram we can realize that in the electromagnetic spectrum, visible light occupies a very, very tiny, small piece of the spectrum, and effectively from 1 eV to roughly 10 eV. Okay, but obviously, as we can see, these numbers are enough to allow electrons to be promoted from the valence band into the conduction band, and this is why light irradiation increases, if you like, the conductivity of materials. Okay, let us have a look now in more detail to doping. So by doping we mean the introduction of impurities into a crystal. So if you are talking about silicon, potential impurities we could look to use is, for example, boron, as we anticipated previously, or for example phosphorus. So boron would be an acceptor dopant, while phosphorus would be a donor dopant. The reason for this naming is that has to do with the fact that boron is in group 3 while phosphorus is in group 5. So boron would effectively create excess free holes, positive charges. So it's a p-type dopant, we could say, while phosphorus, which is in group 5, has more electrons than silicon, so it creates excess free electrons, and so we could say it's an n-type dopant. So let us have a look more in detail to the doping process. So here we have the boron and silicon and their valence electrons. So after hybridization, these valence electrons are distributed in these two ways here. And so this means that effectively when we place boron into the silicon crystal, into a silicon crystal, one electron of silicon remains unpaired. So while that electron from silicon is shared with boron, boron has no counterpart to share with silicon. So effectively the boron atom becomes slightly negative, becomes a slight negative atom, which means leaves effectively a positive charge, a hole, free to move. So this is the reason why boron is an acceptor dopant. So because boron creates excess holes, we call boron an acceptor dopant, and we should then remind that in p-type silicon the holes are the so-called majority carriers, while electrons are minority carriers. This naming has simply to do with the fact that holes will be much more in number than electrons. On the other hand, if we consider donors like phosphorus. By looking at the hybridization of the valence electrons, we can see that phosphorus has an extra electron that obviously cannot be matched by any electron in silicon. So when we place phosphorus in the silicon lattice, all bonds are created with the exception of this extra electron from phosphorus, which basically remains free, and so phosphorus becomes effectively a slightly positive ion, and this electron remains free to move roughly. We will see it in a moment in the lattice. So because phosphorus creates excess electrons, this is a donor dopant, and so we have n-type silicon, where in this way, where electrons are the majority carriers and the holes are the minority carriers. From the quantum mechanical point of view, what we need to remind ourselves is that whenever we introduce an impurity into our silicon crystal, effectively what we are doing is creating an energy state into the forbidden region of the energy band gap of the material. So as we can see here, there are, in this diagram, there are examples of states generated by the different type of impurities we could think of for silicon. And as we can see, phosphorus, for example, creates a state that lies 0.045 eV from the conduction band. On the other hand, boron creates a state that is 0.045 eV from the valence band of silicon. Now, the fact that these states are relatively close to either the conduction band for donor dopants or for to the valence band for acceptor dopants means that with thermal energy, these states that accommodate, for example, for these states of phosphorus, they accommodate one electron, the extra electron from phosphorus. This extra electron can be easily ionized, and so the extra electron can be easily made free, available into the crystal. It is enough to provide it with this 45 milli electron volt of energy to break it free into the conduction band, and the same for the hole from boron. So from the quantum mechanical point of view, the presence of impurities in the silicon lattice has effectively the effect of modifying the Fermi level. So in presence, for example, of donor dopants, the Fermi level would move upward, closer to the conduction band. And we can actually calculate the new value of the Fermi level using these formulas here. So for the case of n-type silicon, so in presence of donor dopants, the formula is this one here, where the intrinsic level is effectively the midpoint of the band gap, and we can see that Kt ln n over ni will give us the new position basically of the Fermi level, and similarly for the is done for the case of p silicon. And so by moving the Fermi level, for example, upward in the case of n-type silicon, this effectively means that at the same temperature, doped silicon will have more electrons into the conduction band than intrinsic silicon. So regarding doping, in the end, few fundamental concepts we should remind ourselves are listed on this slide. First of all, let us remind ourselves that because the lattice constant of a silicon crystal is around 0.2 nanometer, we can quickly calculate that a silicon crystal contains 10 to the 23 atoms per cubic centimeter, roughly. Now, what we've said is that semiconductors that have no impurities added are called intrinsic semiconductors, and we, according to the formalism we've introduced, N is equal P, so the number of electrons and the number of holes, the density of electrons and the density of holes is the same, and is called the intrinsic density, Ni, which in the case of silicon is of the order of this number at 300 Kelvin, and we can also say that N times P is equal to Ni squared. In the case of doped semiconductor, we will use the term extrinsic semiconductor, and obviously the density of electrons N and the density of holes P won't be anymore equal, but we can demonstrate that still this formula is true. And this becomes a very important formula now for the case of doped materials, and this is actually called mass action law. It is important to realize that at any given temperature, if we have Nd is the density of donor impurities in our N-type silicon, not all of them will generally be ionized. So in reality, the density of electrons in an N-type silicon will be generally between Ni and Nd. If, though, the temperature is high enough, and high enough, as we said, means that the thermal energy is enough to promote the electron, the extra electron from the donor dopant into the conduction band, then we can assume that we have complete ionization of the dopants, and so effectively N is actually equal to Nd. We can assume, and so from the mass action law we can actually calculate the density of holes, the minority carriers, through this way. Similar formulas hold for the case of acceptor dopants. Okay, from this point on, I've created these slides where just to have everything in one place, I've put all the relevant formulas that concern the case of intrinsic and extrinsic semiconductors, and allow us to actually see how these fundamental quantities can be calculated, starting from the concepts we've just gone through. So, for example, here we can see how, using the Fermi function, we can actually try to calculate the electron density. So, doing basically this integral here, we define the concept of density of states, which is a concept we will actually see in more details later on in this course, and we can actually calculate the electron density, this integral here on these two functions, and E and Fe. And effectively this corresponds to, if we realize that Ne, the density of state, is actually a function that goes in this way as a function of energy. We will see these things more in detail later on, as we said, but let's take this result for now, and considering that Fe is this green curve here, so effectively it is the product of this the green curve and the blue curve that effectively gives this red area here. So it is the area of this red portion here that provides the actual density of electrons. Or even if we've done this calculation stating here that this is for intrinsic semiconductor, you can see that this is really a general approach, so we can use this approach for any situation. And the interesting thing is that if you consider the special case that the Fermi level is far enough from either the conduction band or the valence band, is at least 3 kT away. This situation is called the non-degenerate semiconductor. Remember that we can move the Fermi level by doping the material. So the more we dope the material, the closer the Fermi level will move either toward the conduction band, either toward the valence band. So by stating here this condition of non-degenerate semiconductor, we are actually, in other words, saying that the material is doped but not too highly doped. Okay, so it's still silicon with a little bit of impurities, and not impurities with a little bit of silicon. That's the point. So in this condition of non-degenerate semiconductor, then we can demonstrate that the formulas we've just seen can be simplified, and they take this form here, and the density of electrons is calculated using this formula here, and P can be calculated in that way. Still, if we are in an intrinsic semiconductor, we know that this n is equal to p and is equal to ni, and the Fermi level can be calculated precisely in this way. The Fermi level is generally very close to the midpoint between the conduction band and the valence band. It's only differences related to the effective mass of electrons and holes that can move a little bit off the midpoint, but these are really tiny changes, tiny variations. Anyway, and here below you can see some values that are relevant for silicon. Now, regarding extrinsic semiconductors, so in the case of doping, we said that not all dopants will be generally ionized. So if we consider a piece of material that is doped both with some acceptor dopants and some donor dopants, charge neutrality can be imposed simply using this formula here. So we have n is the density of free electrons plus the number of ionized acceptor dopants. These are negative ions, remember, and the number of ionized donors, these are obviously positive ions, and so they are added to the total number of free holes, density of holes. Now, in case of, as we said, that for non-degenerate semiconductors, the mass action law is true, and in case of high temperatures that which means that the dopants are all completely ionized, then the charge neutrality condition can be replaced simply with this. And as we anticipated a couple of slides ago, so if we consider an n-type semiconductor, the total density of electrons in this n-type semiconductor is simply effectively the number of dopants, of donor dopants, while the density of holes in this n-type semiconductor is simply given using the mass action law Ni squared over Md. Okay, and here we can also calculate the position of the Fermi level relative to either the conduction band or the intrinsic level. Similar relations are valid in the case of p-type semiconductors. Let us conclude this chapter. So when we have free charge carriers in a piece of material that move under the effect of an electric field, these charge carriers effectively, because of collisions with the lattice and the material, effectively they move at a constant speed, which is called the drift velocity. So if we introduce this concept in our formulas, we can easily say that if the x is the distance traveled by our charge, then this can be written as simply Vd times dt. So now the amount of charge that in time dt travels through the cross-section A of our material is dq equal to n, which is the electron density, the charge density, time q, which is the elementary charge, time the concerned volume of the material, which is A times dx, where we replace dx with this quantity we just written here. We replace dx with Vd dt, and we obtain this formula for dq. So we can calculate now the current flowing through the material simply by taking the q over the t, and from the formula above we obtain that this is actually equal to n q Vd times A. And if we calculate the current density, then it becomes, simplifies even further and becomes this formula here, n times q times Vd. Now it can be demonstrated that the drift velocity is actually proportional to the electric field. So Vd is actually equal to μ times E, where μ is a constant that is characteristic for that material, and is called the mobility of the carriers. Obviously we will have mobility for electrons and mobility for holes. So by substituting, we obtain that J is equal to n q μ E. And so reminding that the resistivity is J over E, we can obtain that the resistivity of a material is generally given by 1 over n q μ. This is for a material that where charge conduction is dominated by electrons. If both electrons and holes play a role, then more generally we can generalize the formula in this way. or we can specialize this formula in presence of dopants that are completely ionized in this as described in this formula here. Okay, this brings us to the end of this chapter. So thank you for listening, and I'll see you for the next chapter.